We have 3 examples for today. The first one involves motion. We're going to have a height function. We're going to deal with velocity, which is the acceleration of height, and then I meant derivative of height, and then we deal with acceleration, which is the derivative of velocity. And that relationship is described in that table on your notes. We have a calculus textbook. The height is given by the equation of an upside down parabola. So for how many actual seconds was the book falling? Well, just to double check, h of 0 would be 400, so that would be at the top of the tower. Then we need to figure out when is the height equal to 0. Okay, so solving that, if I move everything, or move the t to the other side, divide both sides by 4 maybe to make it a little easier. So t equals 5. Our time is not going to be negative, so that's why I'm not including the negative root. So that would be 5 seconds that the book was falling. How many seconds did it feel like to the book? Probably like an eternity. It would be a long way down. For the next section, what was the velocity of the book? The instant it hit the pavement. Now, we know that the instant it hit the pavement was at t equals 5 seconds. To find the velocity of the book, we need to find the derivative of our height. So we have negative 2 times 16. We get negative 32 t. Subtract 1 from the power, that would be 1. And 400 is a constant value. So at the instant that the book hit the pavement at t equals 5, we will get a negative 160. And we want to try to use units whenever we can. 160 feet per second. Okay, you can decide on your own answer for the second part there. What was the average velocity for the book? Now, average velocity, that's going to be our change in our position, okay, the change in h over the change in time for the duration of its free fall. So we're going from 0 to 5. Well, we know h of 0 is 400. H of 5, we didn't figure that out yet, did we? Yes, we did. It's 0. Okay, so we have our change in our position. We're going to have 0 minus 400 over 5 minus 0. And then that would give us 80 feet per second as our average velocity. Now that's a big difference. Technically negative 80 feet per second. That gives us our direction. We know it's going down. The instantaneous velocity is negative 160 feet per second. And the average velocity is only 80 feet per second. It's because it was moving a lot slower in the beginning and then it sped up as it approached the ground. And that has to do with the acceleration, which is the next one. So if we take the second derivative of the height function, or the first derivative of the velocity, they're the same thing, we will get negative 32, and that would be feet per second, or feet per second squared. So the acceleration, it kept accelerating at 32 feet per second on its way down. Now this next problem, you have to remember one important thing. Remember that for a function to be differentiable, it must also be continuous. So when you see a problem like example 13, even though it doesn't say it, you should figure out if it's continuous. All right, so the only place it would not be continuous would be at our part where the piecewise function changes. So let's take the limit as x approaches 1 from the left. So that would be in the 3 minus x part. 3 minus 1 is 2. We have the limit as x approaches 1 from the right. If you put 1 in for each x value, you're going to get a plus b. So that gives us this nice equation. Okay, a plus b equals 2. And then we'll figure out where it's differentiable. We have the limit as x approaches 1 from the left, f prime of x. Think about this derivative is just going to be -1. And then if we take the right-hand side, it would be 2ax. Okay, but x is 1, so it's going to be 2a plus b. And then we have another equation. And now that we have two equations with two unknowns, we can go ahead and set up a system of equations. So we have 2 equals a plus b. We have -1 equals 2a plus b. We could do elimination if we want. I'll just change all my signs here. So I would get -3 equals a, because we have 2a minus a, positive b, negative b. So if a is -3, plug this back into either one of our equations, and we would get b is 5. Okay, for the next one, we're going to do a similar idea. We're going to check to see if it's continuous. We have a parabola and a linear equation, so the only place it's going to be discontinuous is that jump area. So we'll take the limit as x approaches -1 from the left of f of x. We'll get 2bx, but remember x is -1, so we'll get -2b. And then we'll take the limit as x approaches 1 from the right. Oh, it wouldn't be 2bx. I'm jumping ahead of myself here. Let's get back to that. Plug in -1. That would just be -b minus 3. Okay, then +1. I'm glad I caught that. Or -1 from the right side. Wow. Plug in a -1, we get -a plus b. Now, doing what I was trying to do earlier, let's check to see where it's differentiable. We're going to approach -1 from the left of f prime of x. Okay, and so you know, f prime of x, we would have 2bx, this is what I was trying to do, and then a. So from the left-hand side, we would get -2b. Oops, approaches -1 from the right, f prime of x, there we go. And for that we would get a. So now again we have two equations with two unknowns. We'd have -b minus 3 equals -a plus b. We could rewrite that. And we also have this equation, -2b equals a. So in this case, I'm going to use substitution. Instead of writing -a, I'll write 2b. So b, it appears to be -3/4. Oh no, I made a huge mistake. Can you find it? All right, here's what I did. What's -1 squared? That's +1, isn't it? So that's +1. That's +1. Oh man. That's okay, it's calculus. You have big erasers for a reason, right? Okay, back to that. So we have b minus 3 equals -a plus b. -3 equals, if I subtract b from both sides, oh, this just got a lot easier. A is 3. Now our other equation, -2b equals a. Well, we already know that a is 3. So it appears that b equals -3/2. We could plug it in and see if it does work. Or not. You could try it and let me know how you do.